Okay, last time we talked about the Fourier series form, which got us rolling on this idea that e to the ix equals cosine x plus I sine x. Want to talk more about complex numbers, what I is going on, the relationship between complex numbers and plots on a plane, the complex plane it's so called, and that'll be a little bit of fuel as we go into the notion of vectors and matrices and all that stuff later in the semester. For now, we just want to get back to familiarity with complex numbers that I think you probably have seen before, but maybe have forgotten. So remember, here are the three series that we talked about: e to the x, sine of x, cosine of x, and with this magic formula, e to the ix cosine x plus I sine x. Let's see what that looks like in the complex plane. Okay, so let's first get oriented to what the complex plane is at all. So every complex number has a real part and an imaginary part. So we often write that as like z equals x plus iy, where x is a real number, y is a real number. So I times y is an imaginary number. So z has both a real part and an imaginary part. It's complex. And the complex plane is a way of plotting complex numbers. Keep track of both the x bit and the y bit. So let's take an example. Here, this is the real part of z on the x-axis, and here's the imaginary part of z on the y-axis. So let's take the example of z equals 2 plus I3. Z equals 2 plus I3. So we got to go 2 notches over on the real part and 3 notches up. 1, 2, 3 notches up on the imaginary part, and we find that spot. Z equals 3 plus, 2 plus I times 3. Okay. What happens if we flip the sign of z and look for minus z? Minus z is going to be minus 2 minus I3. So where is that on here? Well, we're going to go down to minus I3. We're going to go over to minus 2, minus 2, minus 3. So flipping the sign brings us down here to the opposite quadrant. And look, we went down and over. So it's like flipping over this line like this, like that. Okay. What if we flip just the real part? That puts us over here. This is minus 2 plus I3. That's a sort of weird thing to do, but a really common thing to do is to flip the sign of the complex of the imaginary part only. That is to take the complex conjugate. So the complex conjugate of 2 plus I3 puts us down here, 2 minus I3. Okay? That's how you plot something roughly on this plane. What it doesn't make clear at all is why we would be using a plane to represent things. For that, it's good to think about distances and the square of z, or z times its complex conjugate. So, how big is z? What's the magnitude of z? Well, it's pretty easy to see that the magnitude of the real part of z is 2 and the imaginary part of z is 3, but what's the magnitude of the whole thing of z? Well, what does it mean to even take the magnitude of a complex thing? Well, we could think about the length of this line. That's the length of the imaginary part. We could think about the length of this line. That's the length of the real part. Or we could think about the length of this line. That last one is the one we're going to like to use for the magnitude of z. The distance from z to the origin. So d is 2 plus I times 3, so it's 2 over here and 3 over there. So Pythagorean theorem tells us that it's 2 squared plus 3 squared, which is 4, plus 9, which is 13, is the length of the hypotenuse squared. So this is the square root of 13b. Great. That's not so complicated. how do we get that from z itself? Well, we could take the absolute value of z as the magnitude of the real part squared plus the magnitude of the imaginary part squared. That's what we just did with the Pythagorean theorem. Or we could write z times z star, where star means complex conjugate, which is equal to x plus iy times x minus iy. Let's expand that out. That's equal to x squared plus iy minus ixy plus ixy minus ixy. Those two terms cancel. And then the last two is minus I squared y squared minus I squared y squared. But I squared is just equal to minus 1. So we have x squared plus y squared. That is the same as this. So the way that you get the magnitude of a complex number is by multiplying the complex number times its complex conjugate and just cranking out the algebra from there. But what about the other part of the complex number? The part that's not the magnitude, the part that it's sometimes called its phase. On the complex plane, we could find lots of places that are the same distance from the origin. If I can draw a circle like that, all of those have the same magnitude. So, if I could draw at all a circle, anyway, all of those have the same magnitude, the magnitude of the square root of 13 that we found before. But what's the difference between this one, which is 2 plus I3, and this one, which is 2 minus 2 plus I3, or this one down here that's minus 2 minus I3, or this one down here that's 2 minus I3? What's the difference between all of those? That's the other part of the magic. That's the phase, which is a different part related to the magnitude. And that's where we get back to our e to the ix equals cosine ix plus I sine x formula. Okay, so zooming back to trig, SOHCAHTOA, the sine of an angle is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. But in this case, we have a hypotenuse, which is square root of 13. We have an adjacent to a particular angle. We could take it as this angle right here. And that would be the adjacent over the hypotenuse, would be 2 over square root of 13 for that particular angle. Then here we have the opposite over the hypotenuse. Sine would go with this one. Sine, cosine. Hey, look. Cosine, real. Sine, imaginary. E to the I theta, this thing is giving us a relationship where its real part is the cosine part, its imaginary part is the sine part, and as I change that theta going around and around, e to the I theta would be giving me the location of an angle going around this interface. Okay, what do we get? There's some weird things that come out of that pretty quickly. One, I'm using theta here, but I said x down here. We probably should replace all these x's with thetas, because now we've realized we probably, in this context, we don't want to be thinking of that as, we want to be thinking of it as an angle that's going into this. Also, how did I know that it was this theta, not this theta, not some other angle? Well, I knew that the real part here was the cosine part, which is adjacent over hypotenuse. The adjacent part is the part that goes to the real axis. Okay? So, something that has the same magnitude is this line right here. That still has a hypotenuse of square root of 13. The angle is 0. So, it would be a cosine equals e to the I theta. But we need the square root of 13. So what we really are thinking about in the above diagram is multiplying this whole thing by a square root of 13 as the magnitude. This part is keeping track of the phase, that is where we are around the circle. There's a part that's the magnitude. In this particular case, it's square root of 13, but we could write it more generally as just a real number r for the radius of that circle away from the origin, right? R over here, it's just an r on both sides. Okay, so now this object can plot us anywhere on the complex plane that we want to go, the same way that we were doing with z equals x plus iy. The x part here is r cosine theta. The iy part here is I sine theta times ri sine theta. Now, trig, real trig. How do we get from this form to this form? Okay, with a little blackboard magic, we jumped over to the formulas for both the forwards and backwards directions, going from r theta to xyz and xyz to r theta. Let's go through those. So the more obvious ones is to go from theta and r to xyz, which from this little formula down here, we just take the real part of this side, which is r cosine theta, and that's x. X equals r cosine theta. Then we take the imaginary part of this, which is r times I sine theta, and we set that equal to the imaginary part of z, which is I times y. Both sides have an I in it, so y equals r times sine theta. That's the direction to go that way. Going the other way, we need a little bit of trig to get there. As we've already said, the radius of that circle that we were sitting on was z times its complex conjugate, z times z star, so that's x plus iy times x minus iy, or x squared plus y squared. This makes sense because that's just Pythagorean theorem hiding in there, that you take the real distance along the real axis squared plus the distance along the imaginary axis squared, and that gives you the hypotenuse squared. Cool. Okay, cosine, adjacent over the hypotenuse. The adjacent part is just the x. The hypotenuse is r. But r, we already said, was z times z star, so we can take x, r squared is z times z star, so x over the square root of z times z star, or x over the square root of x squared plus y squared. The sine of theta gives us y over r, opposite over the hypotenuse, y over r. That gives us y over the square root of z times z star, or y over the square root of x squared plus y squared. Now, which one of these is the true version of theta? Well, they're both the true version of theta. You should get both of them back if you use the inverse cosine on this formula or the inverse sine on this formula. Now be careful, sometimes you have to be a little careful about inverse cosines and inverse sines, because you could get shifted by a phase plus or minus a 2 pi in radians, or plus or minus 360 degrees in degrees. So you need a little care, but if you're drawing this out on the complex plane as you're thinking it through, you shouldn't get stuck with any real problems about branch points, because you just realize that those repetitions are just looping around and around the circle more than once.